Hi everybody, this is lecture 3 of our course, and today I'll tell you about a handful of applications of double integrals, and I'll also tell you about vectors. So I'll do a review of vectors, dot products, cross products, determinants of matrices. I'll put everything together. I'll put a summary with everything about vectors that we'll need in our course moving forward. Okay, so let's get started. We'll talk about 5 applications. The first one is that we can use double integrals to find the area of a region R of the plane. So find the area of a region R of the xy plane. So let me draw the region so we can all picture it. So maybe this is here R, this is the region whose area we wish to compute. And then it turns out that the area of this region can be computed as the double integral over the region of the constant function 1 with respect to dA. Okay, so so that formula is correct, but there are 2 ways to understand why the integral gives us the area. So the best way to think about this is using the Riemann sums approach to integrals. So integrals can be defined as a limit of Riemann sums. So to get a Riemann sum, you first subdivide the region into a bunch of little pieces, and then you pick a sample point in each piece. And if I have a piece and a sample point, the things we'll be summing will be the product of the area of the piece with the value of the function. In our case, our function is constant and equal to 1. So we'll be multiplying 1 times the area of each little piece and then adding over all pieces. And the result is so if I add the areas of all pieces in the subdivision of the region, I'll just get the area. So with the Riemann sums interpretation, I'm adding 1 times the area of each piece in the subdivision of the region. That gives us the area. So every single Riemann sum gives me the area, and so the limit of the Riemann sums, which is the integral, also gives me the area. Now there is another way to see this, and this relates to the first interpretation of the double integral that I gave you in lecture 1, and this other way is, so that first interpretation had to do with the volume below the graph. So here the function we have is the function f of xy equals to 1. So the graph is just this vertical slab. The height is 1, and so the volume, so the double integral, according to lecture 1, gives you the volume below this graph. Now this region between the graph and the xy plane, this 3D shape, this 3D solid has the volume of the solid is the area of the base times the height, but the height is 1. So the volume of the solid is equal to the area of its base, which is the area of R. So to repeat that, the volume of the solid is the area of the base times 1, which is just the area of the base. Okay. So for this application, we can think both in terms of Riemann sums or in terms of the volume area of the volume below the graph. But for all other applications, it'll be, we should think of them, I advise that you try to interpret them using the Riemann sums interpretation for double integrals. Let's move on to the next application. So here, the next application is to computing the mass of a planar object. So we can use the double integral to compute the mass of a planar object. If I know the density. So with density rho of xy. Or let me just say the density, we have a density function rho, which tells us the amount of mass per unit area, per unit of area. Right, so the amount of mass per unit area may vary may vary with the position, so may vary within the object. Maybe the object is made of a different in different parts of it are made with different metals, and then the density will change depending on what part you are on the position. Okay, so if I take a little piece of the object with area delta A, and I multiply that by the density, that is going to give me the mass of that little piece of the object. So if I add rho times delta A over the region using a fine subdivision of the region, this is the double integral of the density function times dA, I will just get the mass of the object. So here this object occupies this flat planar object occupies this region R of the xy plane. Okay, so the next thing we can do, and this is the most versatile application of the integral. It tells us what you get when you integrate any function. So by contrast, application 2 tells you what happens when you integrate a density function. Or it tells, another way to put it is, if I give you some function, you can imagine it as some sort of density, and then you can think of the integral as mass for that density. That's sometimes helpful. But application 3 is more versatile. So it tells us that we can use double integrals to compute the average value of a function f of xy on a region R. Right? So if I give you a function, in a region, so for each point in the region, I get a value. I get a value of the function, right? For each x and y in R, I get a number f of xy, and we can really think about the integral. So the average value of f over R, that's equal to the area of the region multiplied by the integral over the region of the function. Okay, so let me put this in a box and let's talk and reflect about this for a second. So what's going on here? Maybe it would be perhaps more honest of me if I told you that the right-hand side is a sensible definition of what I mean by average value on the left-hand side. So I'm saying, so here's the problem. I have a region and a function, and the function has infinitely many, takes infinitely, in general, it'll take infinitely many values on this region. For each point in the region, you'll get a different value, and the region has infinitely many points. So how do you take the average of these infinitely many values? And so there are a few things that we require of the average. It should be between the minimum value and the maximum value of f in the region. I mean, that's one requirement that this definition certainly satisfies. So I do this in the notes, but you can. I don't want to get that into that now. So let's look at what this is doing. So we're doing a double integral, which is to compute this number, which I'm calling the average of f. I'm doing a sum over the region of all the values of f, but I'm multiplying each value by a little area, by an infinitesimal area. Right? So if I were just adding infinitely many numbers, positive numbers, that would give me infinity, but here I'm just multiplying each one by a very, very small, by an infinitesimal, something infinitely small, you can think. And that gives me a finite number, and then at the end of this, I'm dividing by the area of the region. So here's how we should think of this. So the integral on the right, we should think of it as a Riemann sum. So we're breaking the region R into a bunch of little pieces, taking the value, so taking a sample point in each piece, seeing what's the value of f in that sample point, and then you multiply that. So I'm going to say that's the value of f in that little piece, and I'm going to multiply that value of f, the weight, by a certain weight, and that weight is the area of the piece. So I'm doing a sum over all pieces of a subdivision of R, of the values of f multiplied on that each piece, multiplied with a weight, and the weight is the area of the piece. And at the end of it, after doing playing this game, I will divide by the total area of the region, which is the sum of all these weights, little dA. Right? The area from application 1 is the sum of all the dAs. So here, So when we do this integral, we're weighting the values. We're really doing a weighted average of the function over this region, and the weights we're attributing to each value of the function is the total area in the region where the function takes that value, roughly speaking. So this is akin to saying, to computing a grade, so a course grade, like we do in our class. So the grade would have components homework, midterm 1, midterm 2, and final. And then the homework will have weight 10. The second midterm will have weight 30. First and second midterm will each have weight 30, and the final will also have weight 30. So you just multiply the scores in each of these exams, and then you divide by the sum of all these weights. So the weights are 10, 30, 30, and 30. So you divide by 100, and then you get the weighted average of the scores in the exams. So here we're doing a similar thing. We're multiplying the values of the function by certain weights, by these areas of little pieces of the surface, and then dividing by the sum of all the weights, the sums of all the areas of pieces of the surface. All right. So this is a sensible thing to do a lot of the time. But sometimes we may wish to, instead of, a lot of the time we may wish to to use a different weighing scheme. So if I have a density function, so for example, let's say I have a slab of metal, but it's inhomogeneous, so the density varies, and then and then I can measure the distance at the temperature at each point in this metal sheet. So some parts of it will be warmer, some parts of it will be cooler, but it could be that a small portion of the metal contains most of the weight, and that is in a particular temperature. And when we compute our average, we want the average to be closer to that number rather than the other number. So in that case, we'll use a density to compute the weights. So there's another useful notion of average, which is a weighted average of F over R, and that average is 1 over the mass of the region, and that's multiplying. Maybe I should move to the next line. One over the mass times f of xy times rho of xy dA. Right, so you integrate the function, and the weight you give to each value of the function is the mass of a little piece of the surface rather than the area of the little piece of the surface. Sometimes it's preferable to weight by mass rather than by area. Or let me just note that the word density so this notion of density is very flexible. I could be talking about the region R could be a map of the United States or a map of Washington State, and then rho could be the amount, not the amount of mass per unit area, but the amount of people per unit area. And then I would be giving, so if rho was the populational density rather than the standard mass density, if rho is the populational density, then this average number here would be an average value of F, but where I give more importance to more densely populated areas. That might be suitable for some situations. here I'm stressing the fact that you have to interpret the number that jumps out of the interval. And this is a sensible, you have to put thought into it. You just don't use the number without interpreting it. Okay, so the next application I'd like to show you, let me get another page, comes from physics. It's an example of the previous one. So we can use double integrals to compute the center of mass of a planar region. So let's say I have a region R in the xy plane. The center of mass will be a point in the plane that that for some purposes that sometimes is the position I wish to use when. So for some purposes, if I have a certain mass distribution, for some purposes I can replace that mass distribution by a point mass with located at the center of mass, and then from the point of view of all other masses in the world, or from masses outside of that mass distribution, the interactions will be the same. So for some purposes, you can replace a continuous object by a point mass located at the center of mass. So for our purposes, it's important to the definition of the center of mass is important, and it's natural from the point of view of the previous slide. So the x-coordinate of the center of mass is just the weighted average of the mass of the x-coordinates of all points in the region. So we're doing the weighted average of x times the density function times dA, and the y-coordinate of the center of mass is just the weighted average of all the y-coordinates of points in the region. And the weights are given by mass. The weights are based on mass rather than area. Okay, so next, the next application I'd like to show you is moment of inertia. This one is a little bit more tricky. So I remember when I first learned this, I was, okay, I got a good grade on the exam, but I did forget it afterwards. So I'll just redo the derivation with you, and I hope it'll make sense if you've never seen this, and if you did see this before, hopefully this time it'll stick. I remember seeing this for a second time helped me understand and remember this material better. So I'll do a quick derivation, a quick explanation and derivation. So here's what moment of inertia is all about. It's like mass, but for rotation, right? So mass, by Newton's second law, mass is equal to force times acceleration. So, force is equal to mass times acceleration. So for a given force, if the mass is larger, the acceleration will be smaller. So that's a sense in which mass is a resistance to translation. Another point of view, another way to understand the same thing is imagine that you have an object moving at speed v. Then the kinetic energy of the object, the amount of energy you have to impart to the object in order to get it moving at speed v, is 1/2 of mv squared. Right. So if you have a cart and a roller coaster, and you want to get it moving at a certain speed, you have to build a roller coaster with a certain height that gives you the correct amount of potential energy that will be converted to that kinetic energy. Okay, so mass is resistance to translation, and we can think of this as the amount of energy that we need to impart to an object to get it moving at a particular speed. Now let's look at moment of inertia. So that's resistance to rotation, and it's a factor that tells you how much energy you have to impart to the object to get it rotating at a certain angular speed, a certain amount of turns per second. Now we have to be careful about one thing. So moment of it may be easier to rotate an object. So here on the right, I have a picture of an object rotating about the origin. But it might be easier to rotate the object about its center of mass than it is to rotate it about the object, about the origin or other points of different. So the moment of inertia depends on the axis of rotation. So let me just say that the moment of inertia about an axis is the resistance to rotation about the same, about this axis, about the axis. Okay, let's say, so let's understand how much energy we need to get this region on the right, this planar object on the right spinning around the origin. So let's say the rotation, the rate of rotation, angle, the angular speed is omega. So this is measured in radians per second or per unit time, per the unit we're using to measure time. Okay, actually, let me move this on the side. Now, the amount of energy I need to get this whole object spinning moving in this way, doing this rotation movement, I need to get each, if I break the object into a bunch of little pieces, that's the same as moving each little piece in that way. So let's see the amount of energy we need to move this piece here with that angular speed around the origin. So let's see the kinetic energy for that little piece. So the kinetic energy will be so before I write that down, let's take note of a few things. So what's the mass of the object? So the mass of that little piece, so all this here refers to this little piece. So the mass of that little piece is the density times the area that it occupies. So little piece, a little fraction of the area of the whole region. The velocity of this, the speed of this piece is, well, the distance it goes. So in 1 unit of time, it would go, so the speed is the amount, the distance it moves in 1 unit of time. Now in 1 unit of time, it will go omega radians. So that would be a distance of omega in a circle of radius 1. But it lives, this object, this little piece of the object is moving in a circle of radius r, so the distance it moves in a unit of time is r times omega. So the kinetic energy of the object is a half of the mass of the little piece. The kinetic energy of the little piece is a half of the mass of the little piece times the speed squared. So I'll complete this calculation on the next slide. So the kinetic energy of the piece, I'll call it delta k. So the little part of the kinetic energy of the whole object, from the previous slide, it's a half of delta m times v squared. That's a half. So delta m was rho, the density of the piece, times the density of the object on that that piece times delta, the area it occupies. And then we're multiplying by v squared. That's omega squared times r squared. Let me just rewrite this. So that's a half of r squared rho delta a times omega squared. So this number here is the moment of inertia of this little piece of the object. The moment of inertia of the whole object is given by an integral. It's given by an integral. So the moment of inertia about the origin, all denoted by I 0, 0 denoting the origin, is equal to the double integral over r of these little inertia contributions from different pieces of the surface of the region. So that's double integral of r squared times the density function, let me draw a better row, times dA. So here it is in the box. So with this definition, the rotational kinetic energy so the amount of energy you need to get the object moving in this with angular speed omega is a half of I0 times omega squared. So you see that by comparison to, so in translation, we would have a half of m times the speed squared. Here we have a half of I0 times the angular speed squared. So the moment of inertia I0 plays the same role as the mass. So it's a sort of inertial quantity associated to the object, but it relates to rotations rather than translations. Okay, let me delete the comparison here and move on to do a calculation. I should actually, before I move on, let me just make a remark because it figures in the homework. So this derivation gives us the moment of inertia of the object around the origin. We could also rotate the object about different axes. For example, this object over here, we can rotate it not just around the axis, but we could in principle rotate it also around the x-axis or around the y-axis. And then the same derivation would go through, but then you have to get the formula for the moment of inertia about those axes. So about, let me just get the inertia about the other axes, about x, y axes. You just have to replace r squared so r should be the distance from the axis of rotation squared. So the distance, so for the moment of inertia around the x-axis, that's the double integral of the distance from the y-axis, the x-axis squared. The distance from the x-axis is y squared times rho dA. And to get the moment of inertia around the y-axis, it's the same integral, but then you use the distance to the y-axis, that's x squared times rho dA. So these formulas also show up in the homework. Okay, so next I'm going to do an example of a calculation of a moment of inertia of a certain shape. This calculation, I'll do it using polar coordinates. So it'll be a good example of a calculation using polar coordinates. But before I get to that, let me just mention that the derivation that I just did is not something you should expect to see on an exam. It serves to give you perspective, but in this class, sometimes I'll just say something that to inform you. So I think it's appropriate for me to cover a few things that may be slightly tangential or harder than the core material if it serves to inform you. Anyway, so don't worry about this stuff on exams. So I may ask you to compute this a moment of inertia, but that would just amount to using the formula, just looking up the formula and doing it. Okay, so let's do that example of a calculation of a moment of inertia. So that will be an example calculation of a double integral. So this problem asks us to compute the moment of inertia of a circle around a point. So we have a disk. How good does this look? Let me try to use the helper. Okay, this is much better. So we have a disk, and our job is to compute the so this disk has a certain radius, maybe a, and our job is to compute the moment of inertia of this disk about a point in the boundary circle. Now, so that's the problem statement. Compute the moment of inertia of a disk of radius a with constant density. Let's say the density function is just equal to 1 everywhere. So it's 1 unit of mass per unit of area. So you can just forget about it. Our job is to compute the moment of inertia of this disk with respect to a point in the boundary circle. So here's how we're going to start going about this problem. We're going to choose coordinates that help us. So our coordinate system is going to help us. I'm going to shift my view a little bit and suppose that the origin of the coordinate system is the point we're interested in. I can always set up my coordinates in this way. And I will assume that the y-axis is this vertical line over here, and that the x-axis is this horizontal line over here. Okay, so I chose a coordinate system that will play nicely with our problem. And so now we want to so with this setup, the moment of inertia we wish to compute is I0. That's inertia around the origin. So the thing we wish to compute is the integral of r squared times the density times dA. Now let's get to it. This is going to be a tricky calculation using polar coordinates. Let's start setting it up. So we're integrating. We'll do it as I said using polar coordinates. So we'll have integrals in theta, an integral in r, and then the original function r squared times 1, which is just r squared, multiplied by dA, which is r times dr d theta. Now we have to get those bounds. So things start to get tricky right away. So what are the correct bounds for theta? Right. So certainly there is no for theta larger than pi over 2. So here it's at least pi over 2, but it's smaller than 3 pi over 2. I mean, there's no theta over here. Theta is certainly in some range between minus pi over 2 to plus pi over 2. Now, what's the correct range for theta? You might say, okay, maybe we start at 45 degrees. No, that's not going to work. Minus pi over 8 to plus pi over 8. None of these lines will work. We actually, in this example, should start at minus pi over 2 and stop at pi over 2. So we should start at this angle and stop at this other angle. The reason being, if I use any other angle, I'll get a line that's not the tangent line. I'll get a secant line, and so I'll be missing part of the disk. So the reason I'm going from minus pi over 2 to pi over 2 is because this line here, the y-axis, is tangent to the circle at that point. Okay, now let's fix an intermediate value of theta, maybe this one. Let me delete that. Put the marking back on. This is A, this is 2A. Now I fixed an intermediate value of theta between minus pi over 2 and pi over 2. And I have to understand, so when I fix that angle and I shoot out a ray with that angle, R immediately enters the region. So the lower bound for R is 0 because I entered the region immediately when R is 0, and I leave the region at this point. Question is, what is R here? So there is one way to see this. It's not the best way. Okay, it's not as reliable, I would say, but if you use arcane knowledge from plane geometry, you'll find that this triangle is a square triangle. The way to see this is by subdividing it further along this line, and then you'll see that this is A, and this is A. So these two sides are the same. Anyway, let me just delete all that. if you know plane geometry, you can figure out that this angle here is a right angle, and therefore this side over here, this length over here is equal to this hypotenuse multiplied by cosine theta. So that would be 2a times cosine theta. Right, so that's the moment when the ray leaves this region, this circle. So that's 2a cosine theta. I'll show you a better way to get this upper bound in a second, but first let's see what the integral is going to look like. So this is an integral for theta going from minus pi over 2 to pi over 2 of the integral inside is the integral of r cubed. That's r to the 4th over 4, evaluated from 0 to 2a cosine theta. Oh, I missed a d theta at the end. Times d theta. So that's the integral from minus pi over 2 to pi over 2 of 2a to the 4th power. Okay, let me bring out the constants. So I have a quarter and 2a to the 4th power. So 2 to the 4th power is 16 over 4, that's 4, times a to the 4th power, that's there, and then multiply by integral of, so we're integrating cosine to the 4th power d theta. And if you do this, so I'm going to leave you guys with some homework, but if you do this integral, it turns out that you get 3/2, so the moment of inertia for this circle around the point in the boundary circle, for this disk, for rotation about a point in the boundary circle, that's 3/2 of pi times a to the 4th power. So if you use, use some software to compute integral of cosine to the 4th power, or you really, put some time into it, you'll get this number. So let me just tell you what you need to know. So I won't do the integral of cosine to the 4th. I could, but I don't want to bore you. Let me just tell you the key idea that you need to do this integral. So the key idea, the key fact to remember is that, and you need this fact when you integrate cosine squared, the key fact is that cosine squared is 1/2 of cosine 2 theta plus 1. And so let me just emphasize that I have an exponent over here. So cosine theta squared is that, and so cosine theta to the 4th power is this right-hand side of the 4th squared, right? Cosine theta to the 4th is cosine squared. Now cosine squared is this, and if I square that, I'll just get cosine 2 theta squared. And cosine 2 theta can be simplified using this formula again, and then you can do the integral. So it's not very pleasant, but you can do it. Now, to conclude this calculation, let me show you how we get another way to get that on the circle r is equal to 2a cosine theta. So here's how we're gonna get this. So I know an equation. So the points on the circle, so r equals something in terms of theta is an equation involving r and theta that describes this circle. So here's how we can get that equation. We just start from an equation that describes the circle in terms of Cartesian coordinates, and then we write everything out in polar coordinates. And then we have to translate the equation to polar coordinates. So here's how this works in this example. So what's the equation for this circle in Cartesian coordinates? It's x minus a. So it's like, let me just write the equation and tell you. It's x minus a squared plus y squared equals a squared. Right, the equation of the circle the equation for a circle around the origin would be x squared plus y squared equals a squared. This comes from Pythagoras' theorem. Right, that's the set of all points that are from a distance whose distance squared from the origin is equal to a squared, or whose distance from the origin is equal to a. Now, if I want to move a circle around the origin to a circle around the point A0, I just, subtract A from X and 0 from Y. And then I get the equation I showed you. Okay, now let's work this, let's expand this a little bit. So I get x squared minus 2ax plus a squared equals y squared, sorry, plus y squared equals a squared. Now let me cancel a squared from both sides and move, 2ax, I get that 2ax is equal to x squared plus y squared, just rearranging. Okay, now let's write, now that I've simplified this equation a little bit, let me rewrite it using polar coordinates. So on the left, I get that 2a times r cosine theta is equal to r squared. And so this equation here is satisfied for all points on this circle, because it's just the original equation for the circle, but translated to r and theta. So if this is true, then this is true, because the two equations are saying the same things but in different coordinate systems. So the circle is really the set of all points in the plane where this equation is true. Now, away from the origin, if I ignore the origin, I can, the equation in the box is satisfied if and only if it remains true if I divide by r. And also at the origin, so if I divide by r, so away from the origin, I can divide both sides by r and I get an equation, I get this equation over here, which says that r, let me delete this, because let me delete the box, because the equation I really want is this, that r is equal to 2a cosine theta on the circle. This is true for all points, 2a times r cos, just a sec. Yeah, on the circle minus at the origin. Whew. Okay, and this equation inside this box is exactly what I wanted. The description that I gave you at the beginning of the lecture, that r is equal to 2a. And that's what came out in this upper bound for the integral and led to the number we got at the end. All right, so this example shows that we're dealing with a rich subject. So double integrals, have significant connections to physics, and setting them up involves usually interesting geometry, algebraic manipulations. So you guys have your plates full for the next few days. All right, I feel that this lecture has been going for long enough time, so I'll stop things here and start next lecture with the review of vectors that I promised at the beginning of this lecture. So I'll see you then. Thanks for listening. I'll see you guys next time.